Let's push the button, shall we? Okay, good night everyone. We are at another episode of Dan Does Data. We're opening a new series tonight. I want to start playing more with recurrent neural networks. I think they're cool, but I haven't looked at them much. And to that end, I would like to attempt to generate text that looks sort of like Shakespeare. So other people have done things like this, certainly. If you've been on the internet, you've probably heard of this char-rnn piece of software, neural network, whatever you want to call it. And lots of people have used this to do all kinds of things, like model it on famous politicians, or even do William Shakespeare himself, or copy other things. So you can probably just use char-rnn yourself if you've got Torch, or it even has some other options. Hey, it's even got Tiny Shakespeare. What do you know? That's kind of cool. But I want to do it in Keras, and I want to have a better understanding of what's going on. So it's sort of a learn RNNs the hard way, is what I'm thinking about. So thankfully, in the actual Keras documentation, there's an examples folder, Keras/examples, and there's an LSTM text generation. LSTM stands for long short-term memory, which is a type of recurrent neural network. Recurrent neural networks are different from others in that the order in which you look at your training samples matters. That there's an inherent time dimension. And to a certain degree, you can make a convolutional net and a recurrent neural net the same if you convolve in time, but that's not generally how people think about it. So for text, there's an inherent time component of certain text comes after certain other text. So we're going to be using this as sort of a guide, this LSTM text generation, but we're going to be fiddling around and trying different things. This is relatively simple. It's about as simple a model as you can get. So we want to try something that's vaguely like that and not quite the same though. And of course, I'm going to be using some Shakespeare. So I have already started reading this in. Tell you what, let's open up the GIMP. So recurrent neural networks in 30 seconds. Traditional neural network, you start, there we go. You've got some information, some inputs. You start computing things, you compute other information, and then you're done. And that's for a given training sample or a given prediction or whatever. In a recurrent neural network, somewhere in the middle here, at your recurrent layer, you save off your activations or some other value you've computed. And the next time you come through to train or predict or whatever, you're going to be using that value in the next layer. So you save off this prediction because this is some history that you care about. And then it becomes just another feature for you to save. So you could just make your neural network like twice as big, for example. And so you've got all the input features for the current neural net and all the input features for the next time slice. But you want these to be the same for every time, so that doesn't really make sense. And that's a lot of extra computation. So the recurrent part of this is what makes that a little easier. So it freezes all the weights for each step. A lot of how recurrent neural nets are actually implemented, however, is to say, all right, well, I'm willing to look back, 8 time steps, and you unroll the entire network, essentially. And when you go to train, you'll look at 8 things at once and do the back propagation on each one through time. So you can sort of, you've got this first input over here, it back props, it computes something, and then you've got the next one, and so on and so forth. TensorFlow does have dynamic RNN, which I think tries to be a little bit smarter, but we won't be fiddling with that directly today. All right, let's get started on this. So I've already done some Keras imports here, some sequential, some dense, some activation. This LSTM again I've got. GRU is another kind of recurrent layer. It stands for gated recurrent unit. I don't remember exactly what it does. Essentially, these have special memory inside of them that determines when is the right time to throw away old information and add new information. Whereas like simple RNN is very simple. It's like you always throw out the old information and you put in the new information. One of those things. RMS prop is an optimizer. That's what was in the guide I was looking at, so that's what we used. I don't need get file anymore. Perfect. And I believe I already have NumPy. Perfect. So yes, I have already read in some Shakespeare tests from my font classification set. I had downloaded some Shakespeare, and so now I've got that. Take a look at that. Here's some Shakespeare tests. It starts on the sonnets, From fairest creatures we desire increase, and so on and so forth. However, this has, you'll note, a lot of capital letters, a lot of lowercase letters, a lot of other stuff. These /n's are just new lines, of course. If I went to print this, it would not look so terrible. This looks approximately, yes, that's something you would read in a book, a sonnet. I don't want all those things in all these different kinds of characters. Okay? There's too many. Like, I don't really care about the difference between capitals and lowercase. Maybe you do, but take a look at the set in Python of all the characters I've got. You'll find you've got 84 distinct characters, which is just increasing my space of how many different things I can possibly predict. But if I lowercase everything, I can get rid of 26 of those. And now I'm at 58, which is still a lot. Like, I don't think I really need a right curly brace in my Shakespearean text generation. I don't think I really need a vertical pipe. I'm not sure why those are there. This is a mystery to me. So, like, what are all these various things? So I'm just going to save this to something. And let's join those just to get a good look at them. Alright, so some of these are digits. Let me sort them first. So a lot of these are digits. We kind of do want to have digits, even though it's not critical. You're of course going to want a comma, you're going to want a period. You might want a semicolon, and of course, you need new lines, you need spaces. So let me make a list of allowed things. Well, first of all, we'll just say set of lowers plus set. And what are things we wish to allow? We need new lines. If you don't have new lines in your text, it's going to be super pain in the butt to read. Exclamation points and spaces. Spaces are good. I like exclamation points. That's good. We're going to need some quotes. Do we need single quotes and double quotes? I don't think we do. I'll be honest. I do not think we need both of those. Do I want ampersand? Man, I really don't. I don't want ampersand. You definitely gonna need a comma. I don't think you need a hyphen. You need a period. You need all the digits. 0. Whoop, whoop. There we go. Do I need a colon? I don't think I need a colon. I'm gonna end up replacing all these things I don't like with like some placeholder character, like a space, probably. I don't need underscore. I don't need backtick. I don't need pipe. I don't need this other stuff. So that, I think, is fine. So if that's the allowed set, I can't just add sets? I didn't realize that. Boo. But I can just add strings. And now we look at this. We're down to 43. So now we're at about half the size. And I'm really curious if I really need numbers. Like, I wouldn't think that you would. How often? I guess it sets like the stage of like when you're actually at a place. I don't know. Do you need numbers? Let me, I don't know, 2,000. Let's take a look. Just some of these. Like, most of it is just, this is the next sonnet, this is the next this. Like, in his actual text, he doesn't have much in the way of, he very rarely uses the digits themselves, doesn't he? Oh my goodness. And we've got, so we do use period quite a bit. We do use single quote. Curses. Alright. Single quote will be necessary. Here's a good question. Raw.index. Where does double quote? When does that show up? It doesn't show up until that long into the file. By the way, the file is about 5 million long. I forgot to hit the Reddit button. Oh no. Let's submit that. Okay. Oh, shoot. I did not. Ah. Curses. Alright, well, the Reddit one is screwed up. It's going to get taken down. Doesn't matter. Don't care. Doesn't matter who sees it, who doesn't. So that's what? Not more than 10% into the file. Far less than that. It's like 1% into the file. 100,000 out of 5 million? Yeah. Like 2% into the file. That's actually not that bad. Here we go. What a raw.count. You know what? I actually have from, oh gosh, where's counter? Is that this? No. From itertools import counter. This is, I have to remember there's a counter module in Python. Python counter. Collections, there we go. Okay. From collections import counter. Counter. And then if I say C equals counter of raw, there we go. And now you can see the things that are very small. Like there's only 2 of those, there's 33 of those. You know what? Let's shorten this up a little bit. Raw.lower. Because I know I don't care about those things. Can I sort this? Probably not. No. Okay. So lots of new lines, lots of spaces. Handful of double quotes. Single quotes, far more important. Just 21 ampersands, eh? Alright, let's see. Raw.index. This was this number. So let's take raw of this. I don't know, minus 100. Plus 100. Want to look around. Where do we actually use this? Yeah, and he is actually quoting someone. Does to something something, but then it passes to the next person. I don't know. And it's used a few hundred times. I don't think that's actually that important. Digits. Again, at most a few hundred times, and mostly the 9. I wouldn't be surprised. Oh, not the 6. The 0, the 1. Alright. I think these got to get axed. Whereas, like, there's 10,000 question marks, okay? 10,000. Colon? Colon's getting axed. Semicolon? 17,000 semicolons I don't think I can ignore. What the hoot? Oh, jeez. So that means we're going to use this kind of quotation mark to store our Python string. Yes. That is what we need. So that's the text that we're getting rid of to clean up things and make it a little bit nicer. So I will say that data equals raw.lower raw dot replace, yeah, but you can't do a all occurrence of substring replace. You can't do a trans. Oh, you can do a translate. Return a copy of the string S in which each character has been mapped through the given translation table. Table must implement indexing via get item. Okay, so we just need a dictionary. That's all we need. In fact, we want a default dict. Gosh, now I have to remember where default dict is. Default dict. Ah, that's right. A voice from the distance tells me it's in collections as well. Just like counter. Counter, comma, default dict. There we go. Boom, look at that. So D will be a default dict. Default dict. And I want it to default to a certain value. I want it to default to a very particular string is the thing. There's a new value when a key is not present in get item only. Yeah, oh, when a key is not present. Yeah. So default dict. I want to see if I can do this. First argument must be callable or none. That's not going to work. Not going to work. Okay, that's fine. Hang on. Some strange noises. There we go. Okay. So that's not going to work. I thought I could get away with that. Never mind, never mind. Make a dict then. And it's going to be... What do I want here? K comma V. K comma K. No. Or K in not allowed. 4K in raw set raw dot in set of raw. If K in allowed, else raw dot lower. There we go. Else K comma, we'll put a space in. For anything else, it's just going to be a space. I could put like an X in there, but I think this is fine. Invalid syntax. I thought you could totally get away with if K in allowed. I thought 100% you could get away with an else in a for loop. Python. Let's see. List comprehension. If else list comprehension. Let's take a look at that, shall we? If else in Python's list comprehension. Hey, what do you know? Just in blank, if blank else blank. Okay, so it just comes before what I thought it was. If K. Oh, I don't. Yeah, okay. Blank, if blank. There we go. Look at that. Should be much better. Now D's are dictionary mapping most things to themselves and several other things to spaces. Perfect. Data.lower.translate. D, right? Because string.translate, which I don't actually use every day. Which each character is mapped to the given translation table. Table must implement lookup indexing via get item. A dictionary or list. Yes, okay, there we go. Set object does not support indexing. Raw.lower is not a set, neither is D. D is a set, apparently. Okay. I definitely thought I was not getting that. Let's try that. Invalid syntax. Tell you what, let's just do it the old-fashioned way. We'll just call it dict. There we go. Now D's a dict. Type of D is dictionary. Perfect. Data the first 1,000. Yes, all lowercase. I didn't want those digits. That was foolish of me. I did not want the digits. The digits were not worth it. Redo it. Make everything happen again. And now, length of set of, not raw, of data. 58. Okay, that I'm willing to live with. And that should be length of lower, that should be length of allowed. 34. You're right, there should only be 34 things. What's in set of data? There's still all that garbage. So apparently it did not translate. Oh gosh, is translate in place? Why? No, return a copy of the string which each character has been mapped through the given translation table. The table must implement lookup indexing via whatever such and such such and such. Okay, so if I say A, B, C, D, 1, 2, 3, 4, that translate D. That doesn't do anything. For instance, dictionary or list, mapping Unicode ordinals to Unicode ordinals, strings, or none. This operation ranges lookup there, the character is left untouched. That did not do what I expected it to do. Python string translate. String, common string relations. Yeah, that's what I want. String.ASCII letters. Maybe this will do what I want. String lowercase, uppercase, printable, punctuation. No, 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 no. No, 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 no. Translate. No, not what I want. Make trans. Return translation details suitable for passing to translate. They'll map each character from each character into. Well, that's great. Import string. String.make. Make trans. Right? That's a thing? String object has? Was it string.string? No, it's not in there. Okay, so this is a lie. Is this Python 2? This is Python 2. Show me Python 3. One of these days. Probably that's no longer in there because now it's part of Python 3, part of the base. No. Why doesn't string work in Python 3? It's easier to use string.make. Keys are the ordinals of the characters, not the characters themselves. Ah, mother friggin' come on! Dumb. That's dumb. That's real dumb. If it's a string, it should be the friggin' actual character in Python 3. If I wanted a bytes object, I would use a bytes object. That's stupid. Alright, but the point is, I can use string.makeTrans to do what I actually wanted to do. Jesus. Alright, fine. Alright, so keys equals d.keys, I guess. And 2 vowels. Items, not items, vowels, excuse me. Equals d of k for k in keys. And then dd then equals string.makeTrans because reasons, keys, vowels. Maybe there's a good reason and I'm not. If you know a good reason for why that is the way it is, let me know. I would be curious. Argument 2 must be a string, not list. Oh, I see. Sure, that'll be grand. Again, that's a stupid thing here. Should be any iterable, should not have to be a string. Must be a string if there is a second argument. Cute. Well, what the heck are you going to do if there's not a second argument, man? There's only one argument. It must be a dictionary mapping Unicode ordinals. Oh, I see. It must be the thing that no one would want, is what it must be. I apologize for my distress. I just think this is quite foolish. Alright, keys, vowels, perfect. Lots of spaces. DD is now, gosh, that's dumb. Dumb. But now, data of 1000 is this. And length of set data is 58 still. Because I'm using DD. There we go. There we go. Okay, now we're getting better. So again, this is all just prepping the data. We're not even done prepping the data because we don't need this junk open anymore. What we're going to need to do is consider how long of a string we're willing to look at once when we compute our next feature blob. And so what we will do is we'll have like some kind of max length argument. What the hell is this? Char indices? Oh, this is all the list of all the characters he's got. Yeah, I see. So we should want that. We want that. Although Yeah, that's fine. There we go. So this is our list of all the chars. Ding, in ASCII-betical order, of course. The only true ordering that exists. So yes, we can consider maybe, 40 characters at a time. This step business, I'm not 100% sure what that's doing. But as it is, they're like making groups of sentences, where sentences are several chunks at a time, it looks like. No, it's just that many distinct characters. Actually, what I want to do, so I don't go crazy, is say numpy. No, let's leave it. Let's leave it as a string. The string's fine. Yeah, there we go. So we're gonna have. Let's just try what they have. Let's say max lang equals 40. So we'll be looking at 40 characters at once to try to predict. I believe this is correct, to try to predict the next character. That might not be max lang length chars. Yeah, no, that's right. And so what's going to happen is we're sort of going to need to make the 40 long list for every at every step of the way. And they do that. They do that with this. So you got max length 40. Again, this step, I imagine that's going to come clear as to what the heck that is. Oh, we're not looking at every single possible generation. We're only looking at every third. Because we say length of data, we have 5 million characters. If I'm going to generate a 40 long array for each one of those, now suddenly I've got 200 million. And so now I've got 200 megabytes that I'm storing, which isn't a big deal. We can store 200 megabytes. Who cares? 200 megabytes, however, that's probably a good point at which to have a... that's a good point when you want a numpy array. But they're saying step equals 3 here, so like they're not actually using all the data. That's my understanding. Cut the text in semi-redundant sequences of max length characters. So you can say 5, and now you're only taking 1/5 of the data. And so that's not as bad. So instead of this 210 million, you'd only be talking about 7 million characters. Did I do that right? 5 million times 40 divided by 3. Yeah. 70 million. 70. Off by a decade, as usual. Let's just try that. I think that's a reasonable thing to try. That's not a crazy number of characters. This I want... That's fine. Let's see if this takes forever. Text is not defined. Of course text isn't defined. Because mine is called data. Data. So what we're doing here is this is sort of like the current set of 40 that we're looking at. I to I plus max length. And you want to predict what is the next character. And that's just whatever I plus max length is. Easy enough. Max length is not defined. I could have sworn I defined that. And that takes almost no time at all. And my computer has not exploded. We're not using up too much memory. Perfect. That's always the risk. I suspect this will be better than the image processing problem, where for every line I generated like 1,000 things. Here, for every character, I'm generating 40 things, which isn't as bad. Alright, what are they doing here? They say vectorization. Oh, gosh. For every sentence, for every chunk of 40, which is our different training samples, you need 40 long things, and you need to one-hot encode every single one of those damn things. That's just length chars, and that's another reason we wanted the character count cut. I'll tell you what, let's make the step like 10. 10's probably not good. I can go prime number, 7. There we go. Yeah, that's probably good. So length of sentences, that's how many training samples we have. So 700,000, which you'd want way more for a serious model. And you should have just as many next chars, of course. Ding. Okay, perfect. And then you need to encode all in 1/0. And this is where the blow-up comes from. And this is where I would seriously consider, I don't know, you save a lot of pre-processing time by doing it this way. So what do they call it? He just calls it X and Y. Well, I'm going to call mine, I shouldn't call mine text. Yeah, alright, you know what, X and Y is fine. NumPy.zeros, and you're going to want, how many data points do you have? Which is length of sentences. Comma, how many characters in each one, which is max length, comma, how many different characters do you have, length of chars. That's X. Your Y is length of sentences by 1 by max chars, right? Or just by length chars. You're predicting one character at a time, right? This shouldn't be bad. So x.shape is this. So as you can see, this is blank times 40 times 34. That's getting to be a little large. And we didn't maneuver the D type. NumPy dot, we can get away with uint 8s, can't we? I think we can. Because those are all characters? Yes. Okay, let's do that. Again, X, Y. You got them right there, no problem. What do they do here? I am curious. Oh, that's why he built his char indices business. I see. He made a dictionary of all his things in his chars, yeah, mapping both directions. Let's do that now. And we have chars as well, so we can do the same thing. Now, I just want to get this process rolling. So I am just gonna grab all this junk. Oh boy. Oh, man. So much. I forgot to turn on my... There we go. Okay. So we can do that. And then we can get the model going. Helper function, sample index from probability array. And if we can just get the model set up, yes, I think we'll be good. Yes. And so really, you just want to say, don't want visual, model.fit. What are your x's and what are your y's? You should be able to just put in this y. Yeah. Just say 10 for the sake of arguments. Well, let's see if I can do that. See if I can get this started. If I can get this started, I will call that victory for the moment. And then we will worry about getting a model that's decent later, but just getting the model set up. So all we did here was label the 1/0, the correct 1/0 positions. So that'd be this guy, labeling in the X, and in your target, labeling it correct right there. That's all that is. And this is a very simple LSTM model, which is taking forever to compile, which is starting to irritate me. You know what? I'm afraid I'm going to have to call it a little bit early tonight. But this model will hopefully train, and we at least got the data set up. And not next week. Next week I will be off, but the week after we will continue to study this in a little more detail. I realize it's a little bit short tonight, but that's just the way it goes. I think we've reached a decent place of just reading in the data and getting to the point where we can build some type of RNN model. All right. Stay safe in the data mines. Take care.